Hello, and welcome to our final presentation on the modular 3D printed device for in-home musculoskeletal physical therapy. Due to the COVID-19 pandemic, this presentation will be filmed, edited, and later uploaded online for your viewership. My name is Macko, and I will be presenting for group G04-3-7. Thank you. Imagine this scenario. Tom was working at his home when he fell down and hurt his elbow. His injury was a musculoskeletal injury that requires rehabilitation to heal. Musculoskeletal injuries are injuries that deal with muscles, joints, ligaments, and/or tendons. Tom can't drive, and it is incredibly difficult for him to visit physiotherapists or chiropractors on a daily basis. Tom needs to go through rehabilitation at home, but he can't. Our Capstone project is to ensure that Tom doesn't have to repeatedly visit the clinician every single time. This is where our Capstone project comes in. It is a wearable, 3D printed brace which can be remotely altered via Wi-Fi. The device is composed of 3 separate components: the brake, the brace, and the website. The brace is the part of the device which attaches to the patient's arm, strapping onto the upper and lower arm. The brake is the part that exerts a resistive torque when the patient attempts to move against it. And finally, the website, which allows the clinician to remotely alter the settings and parameters of the brake, alleviating or adding to the value of the resistive torque. Currently, there are no telemedical products available which give the same level of rehabilitation that ours does. Figure 3 shows the final prototype that was developed. Notice that the design of the brace is made to fit each individual patient snugly, so it's comfortable to wear. Also, the new electronics enclosure fits around the patient's arm much better this time around, capturing all the electronics inside the enclosure. With the e-stop much more accessible and the power switch less accessible, the patient has much more control over their own device. The brake mounted at the elbow joint is what will provide the resistance to the patient and is controlled via the electronics. The clinician can change the parameters of the device from their own office, adding a telemedical aspect to this solution. Our solution allows the patient on the left to receive treatment from the clinician on the right, even though they're in 2 completely separate locations. The patient will wear the device, which connects to the Wi-Fi, which transfers readings to the clinician's setup for the clinician to inspect. Likewise, the clinician can then make the changes required and apply them to the brace through Wi-Fi again. The user will then feel these changes to their exercises as they develop through the stages of rehabilitation. Our brace design consists of 3 3D printed brace pieces made of PLA plastic that are connected to an elbow joint by 2 aluminum bars and weighs a total of only 303 grams without the brake installed. The 3 brace pieces were designed in a way that would maximize their durability while minimizing the amount of material required. This was achieved using an elliptical shape to be fitted around the patient's arm. This means that as the patient performs their exercises, the force applied to the brace would not be acting perpendicularly to the body, reducing the amount of stress experienced and increasing its durability. Furthermore, the 3 plastic brace pieces have been designed in a way that lets them accommodate for the other features of the device. For example, the wrist piece has been designed for a small space within its geometry for the installation of the force sensors. Aluminum bars were chosen to connect all the pieces together so they can be shaped to conform the curvature of each individual patient's arm. Finally, the elbow joint was designed to house the MR brake that generates the resistance needed by the patient to perform their rehab. It also contains connection points for the aluminum bars that allow the torque generated by the brake to be transmitted across the device. The MAGNETORHEOLOGICAL brake is used as a scalable resistance for the rehabilitation. The electronics and the software, which are controlled by the clinician, change the resistive torque of the brake. The brake, however, never applies a force to the user, only resists the user's force. This feature ensures that the force of the brake will never damage the user. The brake was designed to achieve a peak static torque of 50 Newton meters. Customer requirements also led to the brake being as light as possible to achieve a mass of 1.3 kilograms, as to not weigh down the user's arm too much. As a quick review from last semester, MAGNETORHEOLOGICAL fluids are a smart fluid which rely on the electromagnetic flux density passing through them to operate. The fluid is typically found sandwiched between ferromagnetic plates. When a magnetic field crosses the plates in the fluid, the ferromagnetic particles suspended in the fluid align themselves with the magnetic field lines. The aligned chains of particles tether themselves to the plate above and below them, creating a completed magnetic field. These long chains of tethered ferromagnetic particles resist the relative motion of the plates. If the magnetic field is sufficiently strong enough, it can actually stop the relative movement of the plates. The MAGNETORHEOLOGICAL fluid is what allows us to scale the resistance levels of the designed brake. After an extensive simulated validation plan for the design of the brake, it was time to actually produce a mechanical prototype. The design quickly went from an idealized design to a realistic design to a 3D model in SolidWorks. The designs were sent out and parts were received back from a machine shop. After receiving all the parts, the team quickly got to work assembling the brake, and this was the most pressing issue. In order to complete a functional prototype, the brake had to be tested before installing it onto the rest of the assembly. The electronics are the link between the brake and the software. They contain the force-sensitive resistors, which measure how much force the patient is outputting, as well as a potentiometer, which measures the rotational position of the user's arm. A potentiometer was used over a rotary encoder, as it better measured the rotation and was far more precise. A hard e-stop button was added to the housing for the patient in case they are uncomfortable in any way during the rehab and feel the need to stop the exercises. All of the electronics are controlled by a single ESP32 controller and powered by an onboard battery with built-in BMS for charging. In Figure 12, you're able to see the software for the patient and for the clinician. The website was enhanced to have a login page, a page for the clinician, a page for the patient, and a page to view all historical data, which can be accessed both by the clinician and the patient. The patient is limited to just seeing the graphs of their exercises, an electric emergency stop, and a rating system for the rehabilitation exercises. The clinician's page was customized to have options to change all the exercise settings. This includes changing between a constant torque exercise or a constant speed exercise, as well as all the parameters included in those exercises. An SD card stores all the data in case it is needed to be accessed in the future. The website is also made to be compatible with any resolution. That means it can be accessed through mobile phones or iPads without any issues. There are several potential causes of failure within this device. While a full-scale FMEA was provided in the progress reports, the following table presents a general idea of the variety and severity of different types of potential failures. These failures can have effects ranging anywhere from no network connection to total loss of functionality of the device. These failure modes were accounted for in our design, and provisions have been made in order to address them should they occur. Since the patient has to overcome the torque to move their arm to perform therapy, it was important that we tested both peak static torque and the peak dynamic torque. Testing the peak static torque was a simple process using a stand-click style torque wrench. The wrench will be set to a specific torque value, and if the brake moves without the wrench clicking, then the set torque would be a higher value. And if the wrench clicked without the brake moving, then the set torque value is too low. This process will be repeated until the value converges to a single torque value. This process would have helped us understand the behavior of the torque under different power inputs. Then to test the peak dynamic torque, we needed lab equipment, which was available and was offered to us by the Health Science Department of the university. Unfortunately, both tests were incomplete due to the restrictions caused by the pandemic. The brake is still in the assembly stage and we have no access to lab resources anymore. A test we were able to complete amidst the COVID-19 pandemic was the response time of the system. The test was done by writing a unique test case into the software. A signal was sent by the microcontroller to the website awaiting a response. The test was completed once the response is received back to the microcontroller. The time taken for the signal to reach back to the microcontroller is twice the response time. After running 30 trials, the average response time was determined to be 37 milliseconds. Since our requirement was to keep it under 100 milliseconds, the test deemed to be a successful one. All other tests are explained in detail in the final report. The process of manually adjusting the brace is still relatively clunky. In the future, using techniques such as photogrammetry to create 3D scans of patients' arms should be explored. This will streamline the custom sizing process of each brace and would allow for a much faster turnaround time from the consultation appointment with a clinician to the delivery of the device. Furthermore, there is potential in creating a library of different brace sizes based on data extracted from various anthropometric tables and providing clinicians access to these reserves. This can reduce the impact of plastic waste this design creates by allowing clinicians to reuse plastic brace parts. As the brake was designed, it was difficult to route the required wiring and avoid potentially straining the wires themselves. An immediate fix for these is the use of slip rings along the output shaft. This completely removes any strain that may occur to the wiring and simplifies assembly. Further, hardened pins were chosen to be used to hold the upper and lower discs in place, permanently affixing them to the core of the brake. This makes disassembly impossible without potentially damaging other parts of the brake. Using fasteners as a replacement would simplify the assembly and disassembly of the apparatus. The electrical housing is currently very narrow, which was intended to keep its form factor as small as possible. However, this was quickly noticed to be an issue. Inside the electronics enclosure, the electronics are pressed inside very tightly, with some components being pressed against each other in an unfavorable fashion. If the electronics enclosure were a little taller, even by a few millimeters, this would alleviate the strain of the components and would help the random short circuit problem that seems to be occurring. The software, though very in-depth, can still use many improvements itself. The biggest change will be implementing a decaying sinusoidal or square wave as the output of the brake. The MR fluids inside the brake have a little bit of hysteresis when the magnetic field is changed, meaning that the stiffness of the brake will be different at 50% if it is moved from 20% to 50% versus moving from 70% to 50%. When sending a signal to the brake, changing the signal to a decaying wave would prevent the hysteresis and would make the brake output more consistent. Thank you very much for listening. If any questions are had regarding the presentation, please do not hesitate to email myself at andre.macko@ontariotechu.net or any of the other group members' emails. Thank you very much and stay safe.